All right, guys. So Unit 3 is all about intermolecular forces. This is kind of our theme that runs throughout the unit, okay? And so what we have, first off, is we have to think about what our intermolecular forces are, okay? And really, our intermolecular forces are controlled by Coulombic forces. Okay, so again, our Coulombic forces, if we remember, the force is going to be proportional to Q1 times Q2 divided by R squared, okay? So if we have these intermolecular forces, right, what we can think about is the strength and how charged the different interactions are being, and then how close the molecules are coming together, okay? So what we're going to start with is actually London dispersion forces, right? These occur in all molecules, okay? And it includes our polar and our nonpolar molecules, anything at all, right? Because what the London dispersion forces are due to this random movement of electrons, okay? So our random movement of electrons, right, normally, say we have two things like this, right? Random movement of electrons, now all of a sudden, our electron cloud kind of looks like this, right? So if that electron cloud looks like this, right, maybe we've got a dipole that kind of points this way. What that's going to do is it's going to interact with this other molecule, and it's going to push those electrons away. So maybe, right, if I try and draw this again kind of the same way, we've got this dipole here. It's going to cause the rest of this one to kind of push away, and now all of a sudden our dipole is pointed that way, right? Our electron cloud kind of distorts a little bit due to random chance, and then it forces another, or a change in another molecule, okay? So this is entirely due to just the random movement of electrons, okay? So then we have our dipole, so London dispersion forces, this is what's known as induced dipole, right? Now we have dipole-induced dipole. So this would be when we have a polar molecule and a nonpolar molecule, or another polar molecule, right? So I'm just going to do polar and molecule, right? A polar molecule interacts with another molecule, and it causes a change in its electron configuration, or a change in its electron cloud. So again, say maybe we have a dipole that points this way, and it comes and interacts with a nonpolar molecule. If it interacts with that nonpolar molecule, right, we're going to change it here. We still have that dipole of one molecule, but now, right, maybe some of the electrons are kind of pointed over this way. So now our dipole, we have a smaller dipole on this second molecule, okay? Our third type of intermolecular force is dipole-dipole interactions, right? So this is going to be polar and a polar, okay? And this is when we oftentimes talk about hydrogen bonding, okay? So what we're going to do first off, right, a polar or a dipole and a dipole interacting, right? What we want is for our dipoles to overlap in a favorable direction. So what will end up happening is the positive end of one molecule will line up with the negative end of the other. So we'll get all of our molecules kind of lined up in the same direction. And if I had another molecule below, right, now my dipole is kind of going to point the opposite way, where the positive end of this one is interacting with the negative end of the other, okay? So we get these interactions where the positive end of one polar molecule interacts with the the negative end of another polar molecule. The reason why hydrogen bonding we kind of care a lot about is because it involves hydrogen, right? And it involves hydrogen having Fon. So when hydrogen has Fon, then it is hydrogen bonding, okay? So what do I mean by that? I mean that hydrogen is attached to fluorine, oxygen, or nitrogen, and it is interacting with fluorine, oxygen, or nitrogen. So we'll show an example here. HF, right? Hydrogen and fluorine. Hydrogen is attached to fluorine, okay? But I also might have another molecule of hydrogen and fluorine, right, HF, interacting. So in this case, right, this hydrogen is attached to this fluorine, right? I'm going to label it molecule 2. This one's molecule 1, right? So my hydrogen of molecule 2 is attached to fluorine, but it's interacting with the fluorine of molecule 1. So this is hydrogen bonding. It has to be attached to fluorine, oxygen, or nitrogen, and it has to be interacting with fluorine, oxygen, or nitrogen. When it does that, that is hydrogen bonding, okay? Next up, we have our ion dipole. Ion dipole, right? This is when we have a full positive or full negative charge interacting with our dipoles. So if I have a positive charge, right, it's going to interact with the negative end of a dipolar molecule, right? If I have a negative charge, it's going to interact with the positive end of a polar molecule, okay? Now, let's talk about our strengths then, because our ion dipoles are actually the strongest, right? The strengths, if we think about our Coulombic forces above, right, we have a full positive charge in ions, right? A full positive or a full negative charge. So we have full positives or full negatives. That means that this charge is a whole number, which means that this force is going to be pretty strong. So our ion dipole is going to be the strongest. Okay? Then our hydrogen bonding is going to be the next strongest. Now the reason for this one is not having to do with our charges, right? If we think about our polar or our dipoles, right, hydrogen bonding doesn't have necessarily a different dipole, different charge on them, but it has to do with our R squared there, the distance between them, right? Hydrogen is really, really small. So that means that our fluorine is able to come in and interact really closely with this hydrogen, right? This fluorine is able to come in really close to this hydrogen. So if it's a small distance between them, then are going to have a strong force overall, okay? So then the next one is going to be hydrogen bonding here. The other thing to think about and always remember, hydrogen bonding is not a real bond, right? Hydrogen bonding is an intermolecular force. And then we're going to keep on going up the list, right? A dipole, we've got always this partial charge for charge 1 and charge 2. So partial, we're going to get a decently strong force. So I'm going to do just dipole. Then we go up here, right? Dipole-induced dipole. So we have a dipole, right? That's going to have a charge here, but then we're forcing that second charge to be to have this induced dipole. It's not going to always be there. So this dipole-induced dipole is not going to be as strong as the dipole. So we'll do dipole-induced dipole. The last part, of course, is our London dispersion forces. London dispersion forces are generally going to be weaker than our hydrogen bonding, generally going to be weaker than ion dipole, and generally going to be weaker than our dipole-induced dipole, right? But I keep on saying generally going to be weaker because, so I'm going to do LD for London dispersion there. The reason why I keep on saying generally going to be weaker is because all of these forces are going to be additive, okay? So the intermolecular forces are additive. So we can have a molecule that has only London dispersion forces, but has lots and lots and lots of London dispersion forces. So it's going to have strong intermolecular interactions, okay? So let's talk then about what these intermolecular forces mean in the next video.